Welcome to the code exercises for chapter 9. And let's start with exercise 1. Seems like a good exercise to start with. A square Q, so here Q is referring to an orthogonal matrix. A square Q has the following properties or equalities. Q transpose Q, QQ transpose, Q inverse Q, and Q times Q inverse are all exactly the same. And all of those are equal to the identity matrix. Now, in the chapter, I explained why this is the case, and the goal here is to demonstrate this empirically. And what you want to do is generate a orthogonal matrix Q starting from random numbers. So that's, the trickiest part. It's not really that tricky, but the only tricky part of this exercise is figuring out how to get a matrix Q, an orthogonal matrix, out of a random numbers matrix. And then after that, you just implement these 4 procedures here, these 4 multiplications, and show that they're all equal to the identity matrix, of course, within some reasonable tolerance for rounding errors. Okay, so now I will switch to Python and I'll show you my solution. So I obtained a Q matrix from applying the QR decomposition to a random numbers matrix. So you can see you start with a 5 by 5 matrix of random numbers. Of course, you could do this for any other size, as long as it's square, because all those equalities that I just showed in the exercise text, they hold for square matrices. For rectangular matrices, it's slightly more nuanced. And QR decomposition gives 2 matrices, Q and R. We're only interested in Q here, so I just request the first output. Okay, so I call that Q, and then here is Q transpose, and here I'm computing the explicit inverse of matrix Q. All right, and then, here I'm just outputting all of these Q matrices that I showed in the formulas. So we can run this, and we expect to get the 5 by 5 identity matrix in all cases. And sometimes you get this minus 0, which doesn't really make sense because 0 doesn't have a negative, it's just 0. But of course, these are tiny, tiny rounding errors. And when we round to 8 numbers after the decimal point, that we still don't get anything. So these are tiny, tiny numbers, but they end up just randomly being negative, which is why it looks like we have -0 here.